Hey everyone, today we're going to talk about the controls of ventilation. This is the third video in a three-part series where in the first video we talked about the central control of ventilation. In the second video we talked about the peripheral controls of ventilation and some mechanoreceptors as well. And then in this video we're going to integrate all of this that we've already discussed so that we can understand better how the different stimuli interact and cause us to breathe. So we just summarize the previous two videos that I made. We know that the increased PaCO2 in the blood leads to increased hydrogen ion concentration in the CSF, leading to stimulation of the central chemoreceptors. This then leads to stimulation of the respiratory centers in the pons and medulla, which then leads to increased respiratory rate and increased ventilation. For PaCO2, it also leads to increased hydrogen ions in the blood, which is also a stimulus for the peripheral chemoreceptors, as well as itself being a stimulus for peripheral chemoreceptors. And then the other stimulus is the PaO2. So these all lead to stimulation of the respiratory centers, leading to increased rest rate and ventilation as well. And essentially, there's three stimuli that's identified here. It's the increased PaCO2, the increased hydrogen ions with decreased pH, and the low PaO2, or hypoxemia. And some specific differences between the central chemoreceptors and the peripheral chemoreceptors are that the central chemoreceptors take longer to take effect, but there's a stronger and more persistent effect, while the peripheral chemoreceptors are faster but weaker, but they do allow for breath-to-breath changes, as remember the carotid and aortic bodies are the main sensors here in the periphery, and they're found on the major blood vessels that come off the heart. So blood that's gone through the lungs comes out of the heart. Instantly you have this feedback where you can sense the PaO2 and sense the PaCO2, or the pH, to then lead to changes in our ventilation. So if we were to just graph out these three variables, and we'll put them on a graph with the y-axis as minute ventilation, and I've kept the minute ventilation the same for all three graphs so that we can compare their effect on minute ventilation. And then on the far left, we've got the PaCO2, so this is blood partial pressure of CO2. In the middle, we've got PaO2, which is blood partial pressure of oxygen. And on the far right, we've got hydrogen ion concentration. And we're measuring our partial pressures in millimeters of mercury. You can see for PaCO2, it goes up in tens from 10, 20, 30, 40, and 50. And then our PaO2 is up in 20s, so 20, 40, 60, 80, and 100. And then our hydrogen ion concentration is in nanomole per litre, and this is just 40, 42, 45, 46. So for our PaCO2, when our PaO2 is 100 millimeters of mercury, which is normal, we can see here in the red line, there's a linear relationship between increasing PaCO2 and minute ventilation. Generally, for every millimeter rise, there's about a 2 to 3 litre per minute increase in ventilation to try and match the rise to then bring it back to normal. So the interesting thing about this graph is we're assuming that the PaCO2 continues to rise, and that's what the minute ventilation would be at that level. But in reality, for every rise in PaCO2, the ventilation increases, bringing the PaCO2 back to normal, and normal is around 40 millimeters of mercury, which we can see here crosses the 10 litres per minute line. And then another interesting point to make is that at the x-intercept, this is called the apneic threshold, and it's generally around 36 millimeters of mercury of PaCO2. And theoretically, you wouldn't breathe if it was sitting around here, as long as all other variables were the same in the blood. So PaO2 was maintained at 100 millimeters of mercury. The PaCO2 was sitting at 36 millimeters of mercury, and there were no other stimuli to breathe. And then in blue, we've drawn the same line, but it's at a steeper angle, and this is representing low PaO2. So what this line is actually telling us is that in conditions of hypoxia or hypoxemia, your sensitivity to changes in PaCO2 is higher. So there's actually a steeper line here, meaning that for little changes in our PaCO2, there's actually greater changes in our ventilation. And this essentially shows the relationship between PaCO2 and PaO2, in that PaO2, when hypoxemia is in place, will make you more sensitive to your changes in PaCO2. but it doesn't quite work in the other direction, where if you have PaO2 greater than 100, you don't really get a desensitization for your PaCO2. Then for our PaO2, in green I have the line representing if you have normal PaCO2 of about 40 millimeters of mercury. And the important point here to point out is that when you're sitting at about 40 millimeters of mercury PaCO2, and assuming that your PaO2 is between 100 down to 60, your liters per minute of ventilation remains the same at around 10. But once you cross below that 60 millimeter of mercury point, so going from right to left, you then notice this dramatic increase in our ventilation. So this is in conditions of hypoxemia. Then you all of a sudden have this hypoxic drive to then breathe and increase your ventilation. Now the same sort of line is drawn if you have conditions of high PaCO2. And again, this shows this relationship between PaO2 and PaCO2, in that if you have a high PaCO2, you have a higher baseline for your minute ventilation. And then the sensitivity to change is much greater, as you can see that it begins to rise more around the 70 millimeter of mercury PaO2 mark rather than less than 60 millimeters of mercury PaO2, meaning that you're more sensitive to conditions of hypoxia. Now lastly, for our hydrogen ion concentration, we can see that it's also quite linear, and at about 5 liters per minute for 40 nanomole per liter of hydrogen ions, and it goes up to about 15 liters per minute for ventilation at about 46 nanomole per liter of hydrogen ions. You can see that the change isn't as great. It's only about 10 liters per minute for this small change in hydrogen ions, but it does represent that there's quite a lot of sensitivity to hydrogen ion changes, as our body likes to keep it in tight control. So we already sort of touched on this, but I just want to point out the changes. So you can see for PaCO2 with normal oxygenation, that for about 10 millimeters of mercury change in PaCO2, you have almost about 15 liters per minute of ventilation change. And then for our PaO2, you can see again for about a 10 millimeter of mercury change, you have maybe about a 10 liters per minute change as well, but it's a bit less than PaCO2, so it's not as strong here. And it really depends at what point on the curve you draw these lines. As mentioned before, the CO2 curve, the CO2 line is linear, where the PaO2 line is not linear. It gets more stronger the more hypoxic you become. And then it's interesting to note that above 60 millimeters of mercury, the line is essentially flat. And then for our hydrogen ion concentration, you can see here that for very little change in hydrogen ion concentration, there is quite a significant change in our minute ventilation, representing our body's sensitivity and desire to keep the hydrogen ion concentration within a narrow range to maintain a normal pH. Summarizing these curves or these graphs, you can see that PaCO2 has increased sensitivity to changes in PaCO2, and as a good control of ventilation, as it's quite linear, the higher your PaCO2, the more you will breathe. While for PaO2, there's decreased sensitivity until there's hypoxia. So once you get hypoxia, and specifically hypoxemia, so less than 60 millimeters of mercury PaO2 in the blood, then all of a sudden there's a significant drive to breathe that forms. And then it's important, this flat bit, because when you have CO2 retainers, for example, they will accumulate CO2 if your PaO2 is maintained. And the importance of this is that if you put supplemental oxygen on these people and you maintain their PaO2, they won't have a significant drive to breathe, meaning that PaCO2 will build up in the blood because they're not ventilating, the minute ventilation is not really increasing. And then once your PaCO2 gets above about 70 to 80, then we know that there's actually respiratory depression. And then it's this negative, like spiraling loop of the patient not being hypoxic, so they're not going to ventilate. More PaCO2 accumulates, and then they become obtunded, and through their obtundation will not breathe. Hence why you would avoid giving supplemental oxygen to chronic CO2 retainers. And then lastly, the hydrogen ions, which I've mentioned in the previous video, is mainly sensed by carotid bodies and not the aortic bodies. They are associated with a low pH, and our body likes to keep hydrogen ions in a very narrow complex, but it's still not a very strong stimulus peripherally compared to the other ones. But it is there and does exist. But in times of, say, metabolic acidosis, you'll have stimulation to breathe from the hydrogen ions directly. But also when you have high PaCO2, there'll be buffering that occurs, and you'll go PaCO2 or CO2 plus water, which becomes carbonic acid and dissociates into bicarb and hydrogen. So these hydrogen ions from the raised PaCO2 will also drive breathing. So that essentially summarizes part 3 of the 3-part series. So we've covered central control ventilation, peripheral control of ventilation, and then in this video we've talked about how the different mechanisms and stimulus will stimulate breathing, specifically talking about PaCO2, which is sensed by the central chemoreceptors and the peripheral chemoreceptors, PaO2, which is specifically sensed by the peripheral chemoreceptors, and the hydrogen ion concentration, which is more specifically sensed by the carotid bodies and not the aortic bodies. If you have any questions, anything you want to add or ask me in the comments, feel free to leave a comment, and don't forget to subscribe, as I'll be bringing out more content around physiology.